our first talk, we are excited to have Sanjaye telling us about string theory, random tensors, and combinatoric constructibility.
Great, thank you very much. Thanks to the organizers for the invitation. So this is the title of the talk. It is based on a sequence of papers with Joseph Benjeloun on tensor models and related mathematics. So since it's a sort of general audience, let me just start with something very basic. So in string theory, we are replacing point-like particles. So this is our space-time, directions of space. Point-like particle is being replaced by a string, and world lines are replaced by world sheets. And in string theory, it is very useful to think about this space-time with a string world sheet embedded in it in terms of a world sheet geometry and a map which takes our world sheet into space-time. And in very simple string theories, this map is restricted to be holomorphic, or rather by restricting to holomorphic maps, for example, we can do calculations of all the physical observables. So one of the great discoveries of string theory is gauge string duality, which says that a string theory can sometimes have an equivalent description as another physical or mathematical system, which does not obviously look like a string theory. So there are the old matrix models where this alternative system is just a theory defined by matrix integration. That's effectively is a zero-dimensional quantum field theory. And the dual theory is one-dimensional strings, or in some sense, less than one-dimensional strings. Another important example is two-dimensional Yang-Mills theory with UN gauge theory at large N. Here you have 2D string theory and two-dimensional quantum field theory. And then we have the famous ADS-CFT correspondence where the string theory is 10-dimensional and the QFT is 4-dimensional. Let me just mention that, please feel free to stop me if you have any questions along the way. So the main subject of this talk will be complex matrix models and tensor models. So here is a definition of the complex matrix model. So we are interested in this partition function, which is defined using integration over complex matrices. Here's a Gaussian measure. This measure and the action here are all invariant under UN. So you have, these are n by n complex matrices. And if you transform Z to UZ, you dagger for unitary U, measure and action are invariant. And the physically interesting observables are UN invariant polynomials, which are polynomials in these matrix variables. We are interested in enumerating them and then calculating integrals of these, or products, integrals of products of these. And these things are called correlators. So we have observables, which are invariant polynomials, and we have correlators, which are integrals of products of these things. So this complex matrix model forms an important sector of ADS-CFT, this last example I mentioned. And also within it, there is a beautiful example of lower dimensional gauge string duality, which is similar to 2D Yang-Mills theory. So in this talk, I will start with this complex matrix model and its connections to gauge string duality. Along the way, I'll talk about belly maps, which are a special class of holomorphic maps. And there is related combinatorics of bipartite graphs, which is one kind of combinatorics related to complex matrix models. But there's also another kind of combinatorics, that of Young diagrams, which also comes up in the complex matrix model, and I'll talk about the relation between the two. And then I'll talk about complex tensor models, where a lot of the ideas that I'll be talking about here generalize to complex tensor models. And again, belly maps and bipartite graphs show up. And now, instead of just having sort of single Young diagrams, you have observables related to triples of Young diagrams and to Kronecker coefficients, which is some combinatoric data related to triples of Young diagrams. And then I'll talk about how using these connections between tensor models, bipartite graphs, and Kronecker coefficients, there is a lattice algorithm for calculating Kronecker coefficients. And then I'll talk about some open questions. So that's the plan. The complex matrix model. So we are interested primarily for motivations from ADS-CFT, primarily interested in holomorphic polynomial invariant functions. So you have UN invariants under this action, which are holomorphic. So there's only a Z here, not Z dagger. And the correlators of interest are things where you are integrating with this measure a holomorphic and you're multiplying with an anti-holomorphic observable. First step is to classify these holomorphic observables. So these observables have a degree, and essentially they are traces or products of traces. These are things that are obviously invariant under this action, and in fact they span the space of invariance that you can build for fixed degree. So here, looking at invariant functions of degree 3, you have trace Z cubed, trace Z squared, trace Z, or just trace Z the whole cube, so different kinds of multi-traces. For n, which is the size of the matrix, when that is bigger than or equal to 3, these are all linearly independent invariant functions. And often in gauge string duality, we will be interested in n bigger than n, but not always. And I'll also be talking about finite n effects. So you see an interesting little counting coincidence here. The counting of multi-traces is the number of partitions of n. When you have multi-traces with a total of n z's, in this case 3 z's, you are looking at partitions of 3, and for every partition 3 equals 3. Here all the z's are in a single trace, 2 of them in one trace, 1 of them in another, and so on. So for every partition there is an observable. Okay. So here's a coincidence. P of n, the number of partitions, is also the number of conjugacy classes in the symmetric group Sn. So this is a counting coincidence, which actually is not just a coincidence. What it means is that these traces if you just write them out using index notation, trace Z is this one, ZI1, I1, I2, I2, and I'm summing over these two indices. Trace of Z square is I1, I2, I2, I1. So the difference between these two is that we have permuted these indices, and we can write both of these in terms of these Zs with indices contracted using some permutation, which in this case is the trivial permutation. Here it's the swap. So in general, at any degree, you can build the invariant holomorphic functions by lining up your Zs, I1 up to In here. This is a typo. And then the indices below are the same, except in some arbitrary order, which is parameterized by permutation sigma. And a simple proof shows that the observable you're getting is the same if I conjugate the permutation. So we can label permutations, observables using permutations, but not all permutations give independent functions. There are some equivalences. Okay, so so basically the degree n observables are related to conjugacy classes of permutations in Sn. And this will also be related to an algebra, which I will get to shortly. So, but this is a rather fundamental thing, why permutations are coming up. We are looking at UN invariants. And whenever you're looking at UN invariants, whether made out of a matrix or tensor or whatever, you're going to have some number of sort of fundamental indices and some number of anti-fundamental indices. And in order to get an invariant, these must be equal. The number of upper indices must be equal to the number of lower indices. So a fundamental fact in representation theory is that if you take this tensor product and you ask how many times does the trivial representation of UN appear here, that number is n factorial. It's related to how many different ways you can contract the vectors here with the vectors here. So n factorial is the number of independent things. There's also a finite, this holds when capital N is bigger than little n. There's also a finite n version of this statement using Young diagrams with a constraint. And these facts follow from Chauvel duality. So it's rather fundamental that there are, UN invariants are related to permutations, but also in physics, you don't just encounter permutations, but equivalence classes of permutations. In that example before, that conjugation equivalence came from the fact that phi is a boson. It's a bosonic field. And this gamma parameterizes permutations of that bosonic field. So good. So we have essentially, we're looking at permutations and equivalence classes. So there are orbits on the set of permutations generated by this conjugation action. These conjugacy classes are labeled by partitions. And if you take all the permutations in a given conjugacy class specified by a fixed partition, you get a sum of observables, which is a convenient thing to think about when you're calculating correlators. So this O sub B is labeled by a partition. And then it is also useful to look at a delta function on the symmetric groups, which is defined to be as a function of permutation, defined to be 1 if this is the identity and 0 otherwise. So using this definition and these things, there are nice formulae for correlators in complex matrix models. So if you take two observables, one holomorphic, one anti-holomorphic, you can write the answer for this correlator, which is obtained by doing weight contractions in the complex matrix model. And what you encounter is a formula in terms of permutations in the first conjugacy class, the second one, and then there's a freely summed one, and there is a power of n, which is directly related to the number of cycles in that third permutation. So we have sums of the permutations subject to this condition, and that has a very interesting geometry behind it. So if you have this kind of sum of the permutations in 3 different conjugacy classes, that is equivalently counting holomorphic maps from surfaces from some genus H to the sphere with 3 branch points, where the branching structure is determined by the conjugacy class of this one and that one and the third permutation. And it is counting it precisely with a weight which is 1 over a geometrical property of this holomorphic map, which is the automorphism group of that map. So this is a very simple kind of mathematical model of gauge string duality, if you like, where you're computing something in matrix model and you have a precise connection to a counting problem of holomorphic maps. And it's similar to the kind of string dualities from the mid-90s. So just to draw some pictures associated with this, we're looking at maps to a sphere. There's some surface with some number of handles h. The map is holomorphic, so locally, if I pick a little region in the target and a little region upstairs, it's a holomorphic map. W doesn't depend on the anti-holomorphic part. So for example, W equals Z. And typically for a given region in the target space, there are n sheets for a degree n map. If I draw a line on the target, there are n different lines, but there are special points on the target, typically where the degree is reduced and these different sheets meet. And the places in the target space where this happens are called branch points. And the structure of the branching above is a geometrical property. And the combinatorics of maps with a fixed set of branch points is related to permutations. So we started with matrix models, and then we arrived at a counting which is directly related to the counting of holomorphic maps with a fixed branching structure. And you some different things like this, you get the correlator in the matrix model. So and the genus of the map is directly related to the cycle structures of these permutations. So these maps in particular with precisely 3 branch points, they have some rather remarkable properties proved by Belli that in fact, any of these maps, can be written by writing equations for a curve and writing equations for the map using some complex variables x, y, z, obeying some polynomial equations. And these equations contain some coefficients which are algebraic numbers. And conversely, whenever you have a curve which is defined by some equations like this involving algebraic numbers, it supports a map to the sphere with precisely 3 branch points. So for this reason, these kinds of maps and their combinatorics is very interesting, has been studied in mathematics. They're also called descent d'enfant, some of the associated combinatorics. So it was found useful to sum over the permutations in a given conjugacy class when we were building these observables. But this is also something you can do purely within the group algebra. So these sums exist in the group algebra, and in fact, they form a basis for the center of the group algebra of the symmetric group. When I consider all possible conjugacy classes labeled by partitions of n, we get a basis for the center of the group algebra of Sn. And this correlator that we looked at, it defines a pairing on the group algebra. And in the large n limit, that pairing simplifies, and it's just given by the delta function on the group algebra. So another aspect of, sorry, I erased back for some reason, pressed the wrong button, sorry about that. So another aspect of the matrix model, which is important in ADS-CFT, is that if you are looking at degree of invariance bigger than n, the traces don't give a good basis, but rather a good linear basis is given by Young diagrams. And associated to these Young diagram bases, there are again some linear combinations in the group algebra, parameterized by representations of Sn and defined using characters of Sn. So summary, there is the center of the group algebra, which carries important information about correlators in matrix models. And it has 2 kinds of bases, one labeled by cycle structures or multi-traces in physics, which kind of determine the branching structure of Belli maps when you look at correlators. And there's another basis related to Young diagrams. So all of this stuff has a nice generalization to tensor models, which is the subject of the next part. So in tensor models, you again have algebras related to the group algebra of Sn. So here's the tensor model I'm thinking about. So take a 3-index tensor variable, and you have its conjugate, and a very similar measure to what we had before, and you have an exponential of this form. Again, we enumerate all possible observables, and then we consider the integrals of these or products of these observables. So again, the first step here is to look at polynomial functions of z and z bar invariant in the un cross un cross un, where we think of this as un as transforming in the fundamental of un cross un cross un. So now the gauge invariant observables again are built by basically contracting indices. So this is z and z bar. So now we build the general observables by taking some number of n of z's and n of z bars. And because we are interested in invariance, these are the kinds of models of interest in the physics, un cross un, we have to contract the sort of the first indices with the first indices. So the first index of the phi's, the black indices are contracted with the black indices, the first indices of the phi bar, the second of the phi with the second, and so on. So the contractions are parameterized by 3 permutations. And again, as before, there is an equivalence because of the bosonic nature of z and z bar. So here you have triples of permutations, and you get an equivalent observable if you multiply on the left simultaneously by the same permutation gamma 1 and simultaneously on the right by the same gamma 2. So these are, triples of permutations subject to this left and right equivalence. They define a double coset, and it is known that functions in this double coset form a nice algebra, and I'll describe more concretely how to think about this algebra. So another aspect of this thing is that one description is in terms of triples of permutations with this left-right equivalence. An equivalent description after kind of a gauge fixing where you use one of the gauge invariances to fix the third permutation is to give the same thing is actually related to pairs of permutations subject to this equivalence where you have diagonal conjugation. You conjugate both by the same element. And this is a known combinatoric description of bipartite ribbon graphs. These are ribbon graphs. These are graphs drawn on a surface with black and white nodes, and the permutation tau1 describes, so basically you label all the edges by the numbers 1 up to n when you have n edges, and then going around the black vertices determines for you one permutation, going around the white vertices determines another permutation. So here you have identity for both. Here you have some cycle of length 3 for both. So this data of two permutations subject to this equivalence defines bipartite ribbon graphs. And these bipartite ribbon graphs are in turn closely related to belly maps. Given a belly map of the kind that I described before, where you have a triple of permutations multiplying to 1, given such a map, you look at the target space and you look at the interval from 0 to 1, look at the inverse image, you're going to get a graph of that kind on the surface. So essentially the counting of observables now in tensor models is related to the counting of belly maps. So, and the counting of belly maps combinatorially is given by pairs of permutations subject to this equivalence. So you have the number of ribbon graphs, I will also call it curly n of little n, which is the number of orbits of permutations in Sn cross Sn under simultaneous conjugation. This is also the number of belly maps of degree n, and it's also the number of bipartite ribbon graphs with n edges. Okay, so great. So now, so we have this nice combinatoric structure to the observables in tensor models, which is related to belly maps, and each of these observables is related to an equivalence class, this kind of equivalence class. So you organize pairs according to these two orbits generated by this action of the group. And for each equivalence class, you can pick a representative and perform, the sum over these diagonal conjugations, which produces certain averages over the group. And these averages have the property that they are elements in C of Sn, tensor C of Sn, which are invariant under diagonal conjugation. So basically, the subspace of this algebra, which is invariant under diagonal conjugation, is a subalgebra. It turns out when you multiply these things, you get other things which are also invariant under this diagonal conjugation. So as a result, we have an algebra, which is a subalgebra of this, with a basis labeled by belly maps, or equivalently by ribbon graphs with n edges. So we have this K of n algebra. And what is the dimension of this algebra? There are some nice formulae. You can just take partitions of n, sum over partitions of n with a weight, which is the symmetry factor of the partition, is one way to describe the dimension of this algebra. Another way is there's another formula where you sum over triples of Young diagrams, and the weight for each triple is the Kronecker coefficient. So the number of times this representation of Sn, tensor this one, contains the trivial representation of Sn. That's the Kronecker coefficient. So that the square of that number appears as the weight, and there are two formulae for the dimension of that algebra. So, so the appearance of Kronecker coefficients in tensor models is very interesting. because these are the subject of an interesting question in mathematics, which is that there are many quantities, in symmetric groups, representation theory, such as the dimensions of E-reps, characters, the Littlewood-Richardson coefficients, which have nice combinatoric rules. You label Young diagrams in some way, you count the labelings that obey some rule, and you get the number of interest. For Kronecker coefficients, no such rule is known for general Young diagram triples. Whereas, of course, we know that number what it is in terms of representation theory, there are character formulae, but any known formula involves positive and negative numbers, which add up in some complicated way to produce this non-negative number. So you would like to know, is there some kind of constructive object analogous to Littlewood-Richardson rule or something, where you count something according to some rules, and the answer is the Kronecker coefficient. So this question has been discussed in mathematics recently, has been of some interest in connection with computational complexity. So from that formula we just saw, it looks like the sum of the squares of Kroneckers is constructible in terms of bipartite ribbon graphs, because the sum of squares is the dimension of this algebra. There's a basis for this algebra in terms of bipartite ribbon graphs. So you just count bipartite ribbon graphs with n edges, and you're going to get that sum of Kronecker square. What about a particular Kronecker coefficient? Can we get that for a given triple? That's a natural next question. So that's the subject of the recent paper. And essentially, we kind of use the idea that we saw in the one matrix model. There's a kind of combinatoric basis of conjugacy classes, and there's a projector basis, and the relation between the two is very useful. So if we develop analogous story for K of n, this algebra I introduced, that gives you the tools to address this question, which I will describe next. So this is part 3. So as we recall, in the complex matrix model, we encountered two bases for the center of the group algebra. One was labeled by conjugacy classes, one by Young diagrams. And the coefficients in the transformation were just characters of Sn. So there were conjugacy classes and there was projectors labeled by one Young diagram. Now there are elements of K of n, this algebra that I described just earlier, shortly before, which are kind of labeled by ribbon graphs, essentially. And there is a Fourier transform that takes you to something labeled by triples of Young diagrams. And the counting of this is exactly the counting that we saw before. For each triple of Young diagram, there's C squared. So there is a basis in K of n labeled by things like this, where these multiplicity labels go from 1 up to this Kronecker coefficient. And kind of, here we had characters. Here you would use something more refined, such as matrix elements of symmetric group representations and Clebsch-Gordon coefficients, which naturally have multiplicities, which are these Kronecker coefficients. And these Qs have in fact been useful in thinking about orthogonal bases for tensor model observables. So just to sort of quickly show you the kind of formula we have for Q, instead of characters, as I said, you have matrix elements. So you have linear operators. If you have some E-rep of Sn associated with some Young diagram, you have linear operators. You can look at matrix elements. And then if you tensor two of these two representations, you can decompose into E-reps again, and there's some associated multiplicity, and there's some associated Clebsch-Gordon coefficient, and these are the things enter there. And using such things, you can construct elements like this, which have the property that they form an alternative basis for this algebra K of n. So these have the property that if I conjugate, take a mu tensor mu on the left, mu inverse tensor mu inverse on the right, these are invariant, that invariant subspace of Sn and CSn tensor CSn, which characterizes K of n. So these give you an alternative basis. So what is interesting for the question of constructing Kronecker coefficients is to think about the space spanned by all the Qs for a fixed triple. And the total number of Qs, tau 1 and tau 2, go from 1 to Kronecker coefficient to the C square of these guys. And we just take a direct sum of all of them. the span of all of them. And that's a Fourier subspace inside this algebra, which is labeled by a triple. So the key now is to find a way to identify these subspaces without really using this formula, because we don't really want to choose bases and define Clapeyron coordinates and so on. Rather, there's another, one can think about an alternative way of identifying this subspace. And there is a nice way to do it. Essentially, you have to just pick out these Young diagrams. So, and these subspaces can be identified using some eigenvalue equations. And how does this work? So let Tk be a sum of the permutations in conjugacy class where these permutations have a single non-trivial cycle of length k, and then remaining 1 cycles. So you have these TKs here, some nice elements in the group algebra of Sn. So it turns out that here's a nice fact about symmetric group algebra of Sn. If you take T2 up to Tk star, where K star typically is not very big, you can use the normalized characters for these guys, character divided by dimension, and these numbers uniquely determine Young diagrams. And this is related to the fact that if you take a finite set of these where K star is not too big, these generate the center of the group algebra of Sn. For example, T2 generates the center up for all these values of n, T2, T3 for all n up to 14, T2 up to T6, all n up to 79. So basically, you can use these T's, which are very nice elements in the group algebra, and these are permutations, and these Q's live in C of Sn times C of Sn. So these T's can act either here, they can act here, or they can act simultaneously on both. So there are 3 kinds of these T operators, and when you apply them to the Q's, you get the characters in the representations R1, R2, or R3. And this equation here, this eigenvalue equation, is insensitive to the tau 1, tau 2. So basically, you can pick up the Young diagrams using these eigenvalue equations. And now the idea is to just work with that eigenvalue equation in the algebra K of n using the geometric basis. As we said, there are some bases labeled by ribbon graphs, and you have these things made of permutations. You can act on these bases labeled by ribbon graphs. They are just some pairs of permutations with some diagonal conjugation and a sum. So when you take these TKs, you act on these ribbon graph basis of K of n, you got other things of that sort. So there is a matrix for this action of these TKs. You can show that this matrix is an integer matrix. And these integers are precisely the number of times the multiplication of elements in this TK here with a fixed element in the orbit R produces an element in orbit S. So these are some integer matrices corresponding to these TKs. When this acts on K of n by left action, the eigenvalues are these normalized characters, and these are also known to be integers. So you have a problem where you have an integer matrix, and you have eigenvalues of that integer matrix, which are known, and they are combinatorially constructible using some known results in symmetric group theory, the Monahan-Nakayama construction. So basically, you can identify these interesting Fourier subspaces using an eigenvalue equation. The upshot is that you have an integer matrix acting on this algebra K of n, and this being equal to 0 gives you defines a subspace of K of n, which is exactly that Fourier subspace, because by construction this is constructed using these T's, which identify triples of Young diagrams. So this integer matrix can be constructed, and then if you want to calculate that null space, you just have to find the null vectors of an integer matrix. It's a large integer matrix, so it's not an easy thing to do. This is of size order n factorial. But nevertheless, it's a constructive thing because there are known combinatoric algorithms for calculating null vectors of integer matrices and finding a basis for the null space. These are known in computational number theory.
Sanjay, you've got about 5 minutes left.
5, okay, thank you. So what's happening then is that we have a space, a space of linear combinations of these ribbon graph vectors. So that's another way to describe K of n. We could restrict attention to real coefficients. So inside this, there are some linear combinations which are integer linear combinations, and that defines a lattice inside this Euclidean space. And what the solution of this set of equation, this matrix equation gives you, it gives you, a basis for a sublattice inside this lattice here. So it's the sublattice defined as the intersection of that Fourier subspace with this lattice. And these algorithms give you basis vectors for the sublattice, and the number of these basis vectors is C squared by construction. So this kind of used the complicated formula for Q, but doesn't really require knowing Clebsch coordinate coefficients. It just requires solving eigenvalue equations using the left multiplication by these central elements in the algebra. So that's the basic thing. So a couple of remarks relating this to physics. This K of n is also a Hilbert space. There is a nice inner product, and these TKIs are Hermitian operators. And as a result, this null vector equation that I talked about is related to finding the eigenspace of a Hamiltonian, which has integer matrix elements in an appropriate basis with known integer eigenvalues. So to actually do this, it's a very big matrix. So an interesting question is to how to do this efficiently. It turns out that this kind of question, this is something of current sort of ongoing sort of thinking with Joseph. Basically, these kinds of large matrix problems, there are techniques from quantum computing that can be applied if the question comes from a quantum mechanical system. So that's a future direction that we are thinking about. Also, maybe useful to say that because the states in this quantum mechanical system are labeled by triples, which correspond to ribbon graphs, and these ribbon graphs are evolving in time. You have the quantum mechanics with these ribbon graph states. So there is kind of an interpretation of these quantum mechanics, quantum mechanical problems in K of n in terms of membranes, because you have strings and then they evolve in time. They span some membrane wall volumes. So there are some interesting questions, and I'll just leave this here and maybe entertain questions if there are any. So I'll stop here.
Thank you very much. We have time for a few questions.
Hi, Lara. I have a question for Sanjay. Hey, Sanjay, it's George.
Hello, George. Yeah.
How are you doing?
Very well.
Okay, nice talk and very nice technology. I just wanted to ask a question about sort of things that the intuitions that we have about large and matrix models, both from the old days and ADS-CFT, as you mentioned. So one intuition is that in some sense, there's this extra dimension coming up, should we say holographically dimensions, which comes out from the density of eigenvalues.
Yeah.
I kind of missed that both in the one matrix model and in the tensor model. And the second related question is the collective field theory, right?
Yeah.
So we could actually write a theory for the density, right, of these eigenvalues. Sure. We could do it in the case that Wadi did with David and two-dimensional Young-Mills or one matrix model. And that, of course, it's very similar, kind of in some sense, to ADS-CFT as well.
Yeah.
So where's that? Where's that?
So this has not, so I guess, the way I presented this, essentially you have a class of observables, these hollow, anti-hollow correlators, and there's a very nice geometrical interpretation of that. So of course, no, so I agree. I did not demonstrate, the construction of the space-time string theory a la collective field theory. I mean, there's a lot to do to really, flesh out this string theory. You can also think about it from a world sheet string perspective. Can I really write down an action with a sphere target which localizes to these belly maps? That's also a very interesting question. A collective field theory approach would also be very interesting. So I think there are several interesting questions. I think this is just a hint that there's something interesting going on of that sort there.
Okay, especially this tensor models, because I'm not sure I've seen collective field theory treatment of that. I know what these guys do in group field theory.
Yeah.
They're mainly kind of low quantum gravity people,
Yeah,
but I haven't seen collective field theory. Anyway, that might be different than the usual matrix model. Okay.
Yeah, but what is interesting, again, so this is in the nature of some interesting hints of connections, and here it's that this sort of complex tensor models is also related to belly maps, which was not a priori too obvious. But again, one should flesh this out in a more physical way. So I think Wati has a question.
Thank you.
Yeah, thanks, Sanjay. Nice talk. So I have kind of two related questions. One is kind of the basic question. So you had this really beautiful story when you have these three permutations, and this connection to descent d'enfant and things is really neat. I guess the first question is, was there sort of a physical motivation for picking the three permutations? I mean, you sort of get one and then another, and then you get the thing which undoes it all to do that. And the second question is, if you went to four permutations, is there other interesting structure to be explored there? Does that make sense?
Yeah. So basically, what we did in the complex matrix model, one permutation labels a holomorphic observable, another permutation the anti-holomorphic one, and you try to organize the large N expansion of that. It turns out that to get the large N expansion, you need products of those permutations, and the number of cycles of the product determines the power of N. That's why we wrote it in terms of three permutations. So yeah, so in a sense, unlike 2D Yang-Mills, where you very naturally get multiple permutations, for this particular setup, you just get the ones with three. So yeah, it's a little curious, but quite, even for multi-matrix models, quite generically, you run into counting questions like this with three permutations. And which kind of is interesting from the belly map, number theory, algebraic numbers point of view. What was the second question again?
Well, yeah, the second question was just whether it's natural to consider four, like whether there's some framework in which you could throw in one more permutation, and whether that ties into interesting mathematics or anything like that.
Yeah, well, well, aside from 2D Yang-Mills, I don't immediately know where those. Well, so yeah, actually, yeah. So even if you take products of holomorphic operators and one anti-holomorphic, what it turns out that what you get is one branch point with a complicated structure related to the multiplicity of holomorphic things you put in. So very generically, you get three permutations, at least from
this is sort of where you end up, you're saying, because the holomorphic, anti-holomorphic, and then one more that fixes it all up, basically.
Basically, and that happens a lot in this kind of matrix model calculations, yeah.
Okay, thanks, very nice.
We should probably cap here. Thank you for the good discussion. Let's all thank Sanjay one more time. And Wadi, if you could go ahead and share your slides.